the organizers for inviting me to this very exciting workshop. I'm really appreciate it. Today I'd like to discuss the so-called charge transfer fluctuations in heavy Fermion metals and also high TC cuprates. First, I like to discuss a brief of role of balance or charge transfer fluctuation in heavy Fermion superconductors, cerium, copper-2, silicon, and germanium-2 under pressure. Then I'll discuss the similarity of TP phase diagram of high TC, high heavy Fermion superconductor and T doping P phase diagram of multi-layered high TC cuprates. Then I'll show our preliminary result of DP model with 3-band DP models with UDP, repulsion between D and P electrons, resulting in a possible loop current state and marginal film liquid Alavarma. Okay, this is based on this collaboration. The first part is collaboration with these people. Green ones are former one, and the blue ones are now active, and the collaboration is going on. And especially the next speaker, Watanabe, is a key person in this problem. Okay, this is a signature of critical valence fluctuations observed in cerium copper-2 silicon 2 under critical pressure PV. This is a TC and gamma at 2 Kelvin and residual resistivity and A coefficient versus TK. The inverse of TK, the so-called gamma. So shown here, but I'll discuss later. And shoulder of C over T at TC around here. Well, of course, gamma decreases, there's some structure appears. So decrease and rapid decrease of A coefficient at this pressure. That means M star, due to the so-called Kawasaki relations, M star over M decreases rapidly. And according to the canonical formula of Rice, Wade, and Shiba, NF changes rapidly, say for 0.99 to 0.95 here. Actually, recently, it is reported by NQR measurement under pressure. At this pressure, where TC has a maximum, the NQR frequency decreases from the background linear variations. According to the band structure calculations done by Harima, this change is corresponding to, say, 0.99 to 0.95. So, namely, delta A is this value is corresponds to that decrease of M star with 3.9. This corresponds to this kind of variations. So in that sense, this is totally consistent. Another remarkable thing is that cerium copper-2 silver silicon 10% replaced by germanium shows 2 separate domes, and also shows that rapid increase of rho 0, and also the exponent of resistivity shows linear. We will have some theory on the basis of the periodic Anderson model with repulsion between F and conduction electron, UFC. By treating this of slave boson mean field approximation, and we obtain the change of the F electron as a function of level of epsilon F. Pressure, effective pressure is increased EF, so that increase the pressure, NF changes gradually if UFC is 0. But increasing UFC, this changes sharp, becomes sharper and end up the first critical point. So this is a much more solid calculation, one-dimensional DMRG calculation shown in this paper. For mean field for the first order valence transition curves end up with critical point. By using the one-dimensional critical one-dimensional fluctuation, this point changes here, but the similar aspect is reserved. Interesting is that superconducting tendency dominates over SDW and CDW in this region, the Kondo regime near the crossover line. So that it is consistent with this kind of superconductivity appears this critical value of epsilon F. Let me see this parameter. And we discussed taking the fluctuation around the Slave boson mean field, we can obtain the superconducting interaction, which is almost constant up to 1.5 of kf, then decreases. If we take Fourier transform to the real space, this is a strong on-site repulsion and inter-site attraction, which is the origin of D-wave pairing. So how the intuitive picture of why laser resistivity is enhanced so remarkably is like this. If far from the critical point, the effect of impurity is essentially short range, so that it gives no enhancement appeared in the rho zero. But near the charge transfer critical point, the change of the ratio of conduction and F electron extends to infinity, so that this gives a large, highly enhanced laser resistivity. This kind of intuitive picture is also derived by the so-called Ward-Pitaevsky identity, at least for the forward scattering, which means the renormalization by the many-body effect gives renormalized to the proportional to balance susceptibility, del NF over del epsilon F. Then by taking phenometrically the K dependence like this, then in the critical point and in the critical point, this gives a Coulomb scattering. Then laser resistivity is proportional to logarithm times valence susceptibility, which diverges in the critical point. Next, fluctuation is essentially Q independent, so that phenomenologically we can discuss the effect of valence fluctuation to the self-energy. Then, using this kind of almost flat, almost Q-independent susceptibility, we can obtain the imaginary sigma is proportional to T over T at high temperature region. If omega V equals 0, this temperature dependence dominates, which is the origin of the T linear resistivity at critical point. And also, real part gives another enhancement, so that in proportional 1 over V, inversely proportional. M star over M star is given by the so-called Rice-Weather expression times is enhanced. So near the critical pressure, M bar decreases rapidly, but this effect shows some structure here. So in this sense, the series of anomalous properties observed in serum kappa silicon 2 and serum kappa 2 germanium 2 under high pressure can be explained by the so-called critical valence transition or fluctuations phenomena. We also did much more solid calculation on the basis of the same Hamiltonian and calculate so-called particle hole susceptibility for correspond to the charge transfer, FC charge transfer. Then it is shown that it is almost constant up to KF. So that in this sense, the balance transition is almost Q independent, which is very consistent with that. Balance transition is essentially local phenomena because the F electron and conduction electron by energy considerations. Actually, by using the basis of this Hamiltonian, with this Watanabe and myself, developed the mode coupling theory, which explains the resistivity, C over T, and uniform susceptibility on 1 over T1T of NMR. Shows this kind of anomalous exponent. Guzi is a weakly temperature dependent, has weakly temperature dependence, but between 0.5 to 0.7. So there is a series of anomalous compounds which shows unconventional criticality. These criticality almost coincide with the theoretical prediction. This is completely different from three-dimensional anti-fermionic scenario published by Mori and Takimoto, which is this kind of temperature dependence for these compounds. Okay. This kind of sharp valence crossover is observed not only serum kappa silicon 2 and germanium 2, but also serum rhodium engine 5. Actually, recently, these people reported on the basis of the analysis of resistivity. The line of valence crossover line for serum kappa silicon 2 and serum rhodium engine 5 almost coincide. That means in this pressure corresponds to the valence crossover or valence correspond to the valence crossover valence transition. And also, so this is consistent with the theory this paper, which explains the Fermi surface change observed under pressure by Duhas-Fan Alfvén oscillations, reported in this paper. So similarity, TP phase diagram and of high TC, heavy Fermion system, and T-doping phase diagram of high TC cuprate. This is a Kitaoka group developed multi-layer NMR studies of multi-layered systems like this. The advantage of NMR is to obtain the information of electronic state from layer to layer. So outer layer is subject to some disorderedness due to that whole doping rate. But in the interplane, interplane is essentially free from this disturbance. So that in this region, the free true phase diagram is obtained. For example, in this case, n equal 5 and interlayer, this phase diagram as a function of doping rate is like this. So antiferromagnetic phase extends rather high doping state, and there is a coexistent region of antiferromagnetism and superconductivity, which is very similar to the cerium rhodium engine 5. So this is a pressure, this is a whole number, both P, but it's different, of course. So this at least suggests us also in super high TC Cuprate, the charge transfer makes some crucial role. Actually, this is a schematic energy scheme of cerium-based heavy fermion system. By applying pressure, F level is pushed up toward Fermi level of conduction electron. Whereas Cuprate, the in-gap state, charge transfer occurs from P band to the Fermi energy rockets at in-gap state. So if this energy changes as a function of doping, the similar physics is expected. Actually, this is a very old calculation, but on the basis of 3-band DP model, and using the Gutzwiller calculations, we obtain the bottom of in-gap state, ED tilde. So depending on the size of UD, this ED tilde decreases as a doping is increased. So in the Cuprate, Fermi energy is pulled down toward top of P band with increasing doping P. This is a very similar effect when for cerium-based heavy fermion. Here, F level is pushed up toward EF here with increasing pressure P. So this is the effect of pressure and doping is a similar effect, both systems. We discussed the charge transfer mechanism processes in high TC Cuprate. We use this kind of DP model with whole picture. And introducing the slave boson to eliminate the doubly occupied state of d electron. Then we take into account also TPP and TPD and UDP like this. And due to the direct hopping, there was a 2 bonding and anti-bonding P band here, there. So 3-band Hubbard, 3-band DP model. Using this one expansion around Nagoya, this is very effective for taking into strong correlation effect. For example, for periodic Anderson model, correct T dependence in the resistivity, namely Kondo-like effect behavior at T over Tk, T is larger than Tk, and Fermi liquid at T is less than Tk. And these two limits is smoothly connected. So that using this kind of technique, we calculated the parameter is like this, and the Fermi surface is corresponding to some nearly LSU. Also, P holds has an in-gap state. Like this is a phase diagram for this is transition temperature of SDW and transition temperature of C charge transfer. And the interesting is that if we calculate the susceptibility for chi charge transfer and spin susceptibility, charge transfer susceptibility is essentially constant compared to the spin susceptibility. And interesting is this part is very flat compared to the SDW susceptibility. And we don't, although we need to finish, but after mode-mode coupling effect, of course, this is a result of RPA. By taking the mode coupling effect, usually if the film surface is similar, has nested nature, this part is very much suppressed. Okay. So it is expected that the nonlinear, I mean, non-Fermi-liquid, the marginal Fermi-liquid behavior expected because this is Q equals 0. This is very flat, just in the periodic Anderson model, the case of periodic Anderson model. And we calculated by GL approximation, GL formalism, we obtain the resultant charge transfer mode. If eta is positive, that this kind of pairing state is realized. If eta is negative, this kind of real component is realized. So this is the final one. Of course, there is a DP hybridization term, but this is a time reversal invariant because this is the I change minus I, but kx and ky becomes minus. So that this is time reversal invariant. For example, in the case of eta is negative, the mean field term is reduced to this kind of expression. This is time reversal symmetry breaking because I becomes minus I and kx and cosine kx and cosine ky is invariant. So that this is a time reversal symmetry is broken. Actually, this state is the same as given by the time reversal broken loop current state like this, which is discussed in this paper in detail. This is a toroidal moment, and which is consistent with polarized neutron diffraction reported by this Burja group. Okay. Yeah. Okay. So let me summarize. I briefly review on the role of valence or charge transfer fluctuations in heavy fermion superconductors, cerium Cuprates, silicons, and germanium, and also cerium rhodium indium 5 case. And there, the similarity of TP phase diagram heavy fermion superconductivity and T doping phase diagram of high T cuprates is stressed. And the final part, we present some preliminary result of DP model with UDP, leading to the local loop current state, which was as advocated and predicted by Chandra Varma. Thank you very much.